Basically, we're going to look here is a couple of things. First one, all titled control specialties, little oddball things. First off, selector switches. If you got an across the line starter, basically the classic switch is a handoff auto switch. What that means, if you flip it into hand, the motor will start and continue to run as long as the switch remains in this position. You are not properly, you should not have any control except in case of a motor overload. Code requires that it stop under that situation. Off position, the pump motor is off, or whatever the motor is running is off, and auto, then the starting and stopping motor is governed by control logic. Now, one of the interesting situations you run into, what happens if you've got two handoff auto switches, like one where the control is, say at a motor control center, and one out in the field adjacent to the motor. And I've seen all sorts of crazy combinations as to how we set that up. Here's what I did, or what we did, and after a bunch of us got involved, and here's what I would recommend. Basically speaking, with this setup, the important thing, if you look at this thing, in fact, I won't even take the time to spend much with this, okay? But if you take a look at it, here's the basis. Motor is stopped if either selector switch is in the off position. In other words, if you select off with either one, motor's out of it. Control logic will only operate if both selector switches are in auto, okay? And they're directly hardwired in such a way that when you flip it into hand, it bypasses the PLC. Similarly with off, when you hit off, the motor starter coil is completely isolated and that motor will not start as long as you're in off. So let's go back to the drawing just a moment. As you can see, to actually start and run a motor in hand, both switches have to be in hand. Or if one is, you can have one in hand and one in auto. That'll start and run the thing in hand, okay? Same thing anyway, basically, it doesn't matter if you're hand auto or auto hand, as you see down the third option. Anything off at either end, the motor doesn't run. And if both are in auto, that's the only time you actually have control logic. And I think we came to the conclusion that was the way to do it. Now, a little comment at the bottom here. A useful feature that works well with wastewater pumps that are adjustable speed driven is a reversing switch. Okay, the variable speed drives will quite easily reverse a lot of them on simply a switch input. So if you have, say, a spring-loaded switch and the pump is clogged, you can try reversing it. May not always help, but sometimes it does, and it's a cheap way to go. Now, same thing here. I won't spend a lot of time, but we're basically describing what happens with the handoff auto switches when used with an adjustable speed drive. And you can read that as well as I can, so I won't spend a whole lot of time on them, but there it is. This is an example of, on the left, the actual control schematic, and in this case, it's across the line and a single handoff auto selector switch. This is the wiring, and if you look, there's a box on the right that says field station. If you look, there's terminals right down, there's a whole row of terminals there. That would be field wiring between, say, the MCC, Motor Control Center, and the field station adjacent to the motor itself. Yes, it's a bunch of wires, but yes, it does give you very good, what I think is safe and reliable, dependable logic. The PNID is a drawing. If people know what a PNID is, and for operations you don't need to know. It's basically how does the process work. It's a language unto its own. And here's another example using a solid state starter, and again, the remote station. Here's an example using a variable speed drive, and again with a remote station, okay? Now, applications. These from here are basically things that a PLC can do, programmable logic controller. Besides being reliable and everything else and capable of a whole lot more volume of control than what relay logic could ever hope for. I mean, I've seen relays at one time that literally within the huge big control panels, you'd have layers, different doors and layers of control relays. PLC can do an awful lot, but it can also do some things that um, go beyond just straight relay. Programmed alternator. At one time, in order to alternate pump operation, an alternator relay was required. And this relay here, and you can read the 47AB 10A, F is 120 volt because we used to use it by the ton. And it was originally made by Furnace, who were bought out by Hubble. Okay, and it was a very reliable. The coil would energize. When de-energized, it would flip contacts. There's a common in the middle and one or the other, and it would flip the pumps. So your typical two-station is the way to alternate. You can do that with a PLC. In fact, you can go beyond that and deal with several pumps. And how it's done is to use a count up command. It's a box that you, much like you have a bit, it's one of the things you can pull up on the screen on the PLC or PC when you're programming the PLC, where it'll pull up a count up. And basically, it'll accumulate input pulses as an addressable total and then reset when so commanded. Every time a pump is commanded to stop, then we will have an input to it. For example, it can count zero. Let's say we've got pumps. 0 is P1, 1 is P2, 2 is P3, etc., etc. And as the count goes up, and those are inputs to the PLC, as the count goes up, at each level you can use an equal instruction, like if it's 2 equals 2, then here's what's going to happen. By the way, never again use pump start. Always when the pump stops. Then when we've got what we want, then we use a reset when we're beyond the pumps to bring it all back and start it again. Let me show you on the actual program. So when a pump stops, you get in that B301, it's just a one shot to make sure we don't get it static. The counter basically is accumulating counts as they go up. And preset is 2. In other words, maximum is 2, which is done. Let's see what happens. When the count is 1, go down to that line 0001. Equal, source A and B. This is an equal command. If source A equals B, and the 0, and to begin with the count will be 0, then it goes through and it'll give you Alt-1, give you one of the pumps to operate. When you get the next time we have a pump shut down, it will count, and the count is now 1. That's what we're looking for. So 1 and 1 equal out, and then that'll energize the second pump, Alt-2, and when we're beyond that, done, the top there, preset done, then reset, we go right back to the beginning, and that's telling the thing to scan, to reset the timer, counter, and there's an end for that command, again, to be circulating around and around and around. So every time something stops, the counter goes up 1, it counts 0, it fires off, or sets up to start one pump, at count 1, fires off, set another one, at 3, the count resets, and the end thing is just a scan line that causes it to continually go through the loop. The end is just always there as a deal to make the PLC operate. So what are we talking about here? Typical duplex pump will have P1, Alt, P2 lead pump selector switch. And in the Alt position, it'll alternate between P1 or P2, or you can select either one of them to be the lead duty pump all the time. We can go beyond that using this counter arrangement, count up. We can have 6 duty pumps and a lead selector switch such as alternate P1, 2, 3, 4, 5, 6, which permits any duty pump to be selected as a lead, or the lead duty pump function can be automatically alternated amongst the units available by going to the Alt position. If an additional pump is called for, the next available unit in sequence will be started. Pump decreasing, the unit that has been operating longest will be stopped. I wouldn't attempt to do that kind of programming. You really kind of have to be into it to do it. I have done it, but it's been a while. But you know that, I guess more than anything, know that a PLC is capable of doing this. Now, again with PLCs, PID and time proportional pulse output control. Now, PID, which is not P and ID as we saw before, which stands for proportional and integral, or well, no, part P and I, getting myself confused. Process and instrumentation diagram. Okay, but PID by itself means proportional, integral, and derivative functions. It's an algorithm that's extremely common and can be explained in mathematical terms, which I wouldn't even begin to try. But basically, what does it mean? Proportional, and this is a way of controlling something. I'll jump into it right now. If you have a car with cruise control, it has PID or PID. Keep making that mistake. PID, no I, no intelligence. PID. The proportional means proportionally more corrective output the further we get away from the desired set point. This will ultimately result in a stable condition, but with the process not at the set point. Let's say you want to run at 60 miles an hour, and the car comes to a hill. Well, as it starts drifting away from 60 mile an hour, you have it put in, give it more gas, give it more gas, give it more gas. Eventually you hit a point where the car is not slowing down anymore because of the hill, but it is not at 60 mile an hour anymore. It's had to decelerate because of the hill. So it's stable, but you're not where you want to be. Then we come into integral, which means periodically we'll add the corrective output so that the process will then be at the set point. In other words, if we've gone up the hill and we've given throttle as it slows down and finally hit a point where the car is not slowing down anymore, but and we've got a proportion between where we are, like 40 mile an hour, not the 60 we want, then integral will look at it periodically and say, whoops, I'm 20 mile an hour off where I want to be, so apply some throttle to bring me back up to that steady at the 60 mile an hour, not the 40 mile an hour. The derivative is simply if you're dealing with a process that changes very slowly. There the reactions are speeded up because you have a slow reaction, so you need corrective input that's fast. Okay, that's PID. Now, dealing with PID, basically there are three values that go into it. Number one is the set point. How fast do I want to go? 60 mile an hour. You get on a car, of course, you get to pick that point, but there we are. Process variable. Where am I actually at? I've set it for 60 mile an hour. Right now I'm at 30 mile an hour. So there's where we're at. And the control variable is the control output intended to correct the process. The controller in the car tells me I need to give it more gas. Okay, so there's your basic PID control data. The set points that are involved, and as we saw before, what PID actually means. Now, PID is a block within the PLC. And you notice a little thing that says setup screen. When you get to that, there, depending at least in my day, 17 addresses that might be, it asks you a whole bunch of questions. One of these is control mode, which has two choices. Error. The error is called direct. And error is the process variable is higher than the set point. This is if you're going too fast. In other words, my car, I'm doing 80 miles an hour. I take my foot off the gas. I really want the cruise control to take me at 60. So the process variable we know is higher than the set point. So we compensate with that error, that direction. Or pumping out of a wet well where the pump speed is the control variable and a higher error requires a faster pump out. Now, the other way is where the error goes the opposite direction, where the set point is higher than the process variable. My car is doing 30 miles an hour. Now I hit cruise control. I want it to be going 60. We know the process variable is lower than the actual. So we then will speed things up. Okay? Now, this is kind of interesting because the PID actually puts out a numerical value which is easily converted to a 4 to 20. For example, if we are trying to control wet well level and we have variable speed pumps, then the PLC, using this PID control thing, will put out an output signal in a 4 to 20 signal, which goes to the variable speed drive, telling the variable speed drive how fast to go. And I had somebody who very knowledgeable would say, well, you, but not all the way, say, oh, you can't, yeah, it's the only way you can do it. The device has to be able to accept a analog signal. No. There's possible to convert the control variable numerical output into a time proportionate output. Time proportion pulse control that can be used to operate, say, a dual solenoid equipped automatic valve. And here you have a valve, and you notice that the closing input to cover has a solenoid. The cover to output for opening has a solenoid on it. There's a little manual, that's all those little bypasses are for testing only, little manual bypasses. But basically, I can control those two solenoids and get the valve to actually control what it is we want to control. Now, converting that PID block signal into a time proportion output is a bit of a dance, but it can be done. And this goes through the steps of basically doing it. And I won't try to walk it, but basically you can see the PID. There's a base timer, which is basically saying how often am I going to go between pulses. In this case, 10 seconds. Every 10 seconds, I'm going to look at the thing, and if I need to, I'm going to pulse one of the other solenoids. So we'll get into that later on in a minute here, other solenoid. And it goes through a whole production as to how this thing is done, but it can't. That's logic, by the way, from Alan Bradley / Rockwell, and it does work. I have programmed it, and it's kind of cool and neat. Now, since this valve can either be, let's say we're controlling flow, you can get the valve to do whatever you want. You can control pressure, you can control flow, you can control level, anything that you can measure that's varying, you can set that valve up to control. It's simply inputs to the PLC. Let's say we're going to control flow. It can either be flowing too much or flowing too little, meaning the error can either be direct or reverse. Remember we talked about that? We need an input to the block that will both reverse the control mode and also switch the solenoids as needed. This is roughly analogous to a car in the mountains. When going uphill, where the set point is above the process variable, in other words, you're slowed down, it's reverse, and the controller, you would compensate for by pushing on the gas pedal, the CV output, control variable output, to maintain speed, process variable, at the limit, set point. If you go too fast, you simply back off the gas and it'll slow down because you're going up a hill. Okay, fine. But if you're going down a hill, now instead of the gas pedal, you need to worry about the brake. Move your foot to the brake. So we got a different CV control variable output so that we can maintain speed. And in this case, if we're going too fast, which is what happens when you go down a hill, without applying the brakes, so the process variable is actually too high. So that now we're going to direct, and the set point, the speed, we want to maintain a set point. If you're going too slow, backing off the brake will cause you to speed up. So here's how you do that. As part of that one that's basically saying, okay, fine, here's the output. But we have a product that allows us to change from a set point from direct to reverse. Okay? And in doing so, we got one that changes the PID control mode from direct to reverse. Okay? And if we go back to, we should be able to find that fairly quickly. Control variable numerical output. Okay? There is a bit here that allows you to make that flip. I won't waste any more time trying to find it, but it is. So basically what we have here is on the right-hand side where it says change PID control mode from direct to reverse. That's been input to CM, which is actually, going back real quick, it's quite simple. It's actually the CM module, part of the PID tells you is which way am I going with this thing, okay? And we have another part along with that, where if we get to a situation, changing from one to the other, we change which solenoids to use. Like the pulse output at line 0008 can either go to the closing solenoid valve to close the valve down, or if we fall too low, it'll flip to the next line. That B301 below basically will change it so it now will hit the opening solenoid to open the valve in increasing flow. As I say, it can do anything that can be measured, it can control. Pressure, flow rate, level being the common ones. Also allows remote SCADA set point changing and tuning of the PNID. Now, wet well level control with adjustable speed drive. Ground operations, I mentioned this thing about you could have speed where you get down to a point where it's direct because the process variable is normally higher than the set point. What we're talking about, let's say you've got a well and you're scared of over pipe pumping it. And let's say at 50 feet down, that's as much as we want to go down. At that, we want the pump to adjust speed and hold that level regardless of what the demand or income flow is. What will happen is if there's flow more than what is required, then the level will go up, and this thing will constantly tell the pump to go faster and faster, trying to pump it down. And it can't, but at least the pump ends up at full speed. It's only doing the control thing when you get down to that particular point that you wanted to not pump any further. And I mentioned the thing about it screwed up on the point about PID being completely different from P and ID, process and instrumentation diagram. Another thing PLCs have, which can be useful, is a real-time clock. And basically, it continuously runs as long as the PLC is powered or the backup battery is good. And initially adjusted by several addressable status files. There's a file S37 for year, one for month, for day, hours, minutes, seconds, days of the week. And it's just constantly clicking away. And by using an equal, in other words, when it hits that any particular point, then you can have when it hits that, some event happen. Let's take an example like you can see here, there's a range like you can adjust the year, you can set it at, this is how old it is, at 2022, try 2024. You set it at that and it'll just keep, next year it'll go again, next year it'll go again. And the month, let's say you want May, you set it as 5, month 5, but at 12 would be December. You set that. Day, let's say on the 9th day of the month. Hours at 15 hours, we're using 3 p.m. is 15, we're using military time here. Seconds, minutes, 30 seconds. When all those match up, then you can have an event occur, like flush pumps or whatever. And you may want to do that every day. So then you ignore them all except the hours one. And every time, now 15, 3 p.m., you may want to have 3 a.m. At 3 a.m., you go into a flush cycle on the pumps. And as soon as it sees that equal that, boom, off goes the cycle. Here's basically the real time clock. You're setting, talk about equal statements, the desired minute, the desired second. Now, if you want a pulse output, we've set for a 30-second pulse output. And there's basically your whole setup that you can do using a real-time clock. Now, again, get into something a little different, which can be useful and PLCs do. Set point offset. The concept of increasing, now we're almost talking mechanical, the concept of increasing output pressures, flow rate increases to compensate for friction and reducing pressure and thus system leakage when flow demand decreases actually goes back decades. First applied to pressure reducing valves feeding aircraft refueling hoses, so that the pressure at the end of the hoses would remain relatively constant even as hose friction increased with higher flow rates. And this was done by having the remote sensing pressure reducing pilot. You can have them so that they actually, instead of internally sense pressure, have an external port for doing it. And as you see here, it's going over to the throat of a venturi. So as flow rate went up, the venturi throat pressure would drop, and in doing so, the pilot would see that, try to bring it back up to the set point, and thereby opening the valve. So in fact, you're getting more pressure as the flow rate goes up. And doing it that way, in the mechanical sense was an idea that a local guy named Wilf Crane came up with and used it on several municipal systems, and they worked very well. Now, while it can be done mechanical, a better approach is to use a PLC with input from a pressure transducer and flow meter to control pressure. Let me give you an example here. Let's pretend that you had, if you look at the middle of these, let's say you had a constant output pressure from your valve or pump station. What would happen is the flow rate went up, and you can see down below. So we've got booster pumps or PRV on the left. Long ways away, we've got the area we're trying to serve. And if we have a steady pressure coming out of that on the left, you're going to get decreasing pressure as the flow rate goes up. But if you can vary the pressure and have it go up with flow rate, then you'll end up with a constant pressure out in the field. That's called set point offset control. And you can have them done with, there's a number of different ways of doing it, but basically something a PLC can do relatively easy. Now, a little equation that can be programmed into the PLC, and basically what it's saying is the corrected, and it can done it for both system SI metric system and for US unit. Let's start with US units. Here's a little formula where the corrected set point, in other words, what the system will try to gun for, is equal to the set put plus the flow rate in US gallon per minute divided by 1,000 and squared times an offset factor. The offset factor is to allow you to adjust how much of this you want to have happen. For example, let's assume the basic set point pressure is 50 psi, flow rate is 2,000 gallon a minute, offset factor is 3.8. Given these conditions, the corrected set point will be 50 plus 2,000 divided by 1,001 squared times 3.8. You end up with 65 psi. Okay, the offset factor is adjusted as necessary for each application. So by changing that offset factor, you can tailor it for the specific application you've got, but basically that can be programmed into the PLC. And there's the same thing in System SI, and I won't get into it. Another little trick that can be done, and a lot of these I'm just telling you what can be done. I don't want to get into detailed programming. You can actually have the PLC calculate flow rate very accurate. If we're talking, say, constant speed pumps. If you have no flow into a wet well, and you can time how long it takes to pump out that wet well volume, in other words, start, stop, we know what the volume is, nothing's coming in, we can quickly arrive at what the pump is doing. However, if there's inflow to the wet well occurring at the same time, that doesn't work. What you can do is first measure the inflow rate by timing the filling between stop and start, and then adding this to the calculated outflow rate to arrive at an actual flow pumping rate. The easiest way to arrive at the inflow is say, there's the first part of this. Inflow rate is the active volume divided by the time to fill the active volume, okay? But if we do the trick of we've got inflow into the wet well, we can do that plus the refill rate. That's a calculated inflow rate. Add the two together, and that's what actually is going out. And you say, well, what happens if the inflow rate changes? Which it will. The more you do this, the more accurate it gets. And over a period of time, you'll arrive at a very, very, very accurate indication of pumping rate. And it explains more detail on it. At one time, there were devices that actually made to do it. The first I heard of was called the volume meter. But right now, and I think it's still in production, ISCO has a relay called a pump station flow monitor that basically does what I just described. And you can set up the PLC to do this only with one pump. Any multi-pump operation, ignore it. But you can do it for one pump, and it'll get very accurate as to what that pump is going at. And you can see if it's falling off in performance or whatever. Daily average flow rate pumping. Why would we want to do this? The objective of the water pumping should be to minimize energy consumption. Say pumping into an open-ended, say a reservoir system where line friction is significant. Pumping at the lowest continuous practical flow rate, regardless for how long, will yield the lowest overall power consumption. In other words, you're trying to avoid friction. With wastewater, what you're trying to do there is have a constant flow into the wastewater treatment plant because they operate best with a steady given inflow rate. This will work if you've got a significant storage capacity upstream of the feeder pump station wet well, say a long force trunk main. By varying pumping rate by the use of adjustable speed drive, it is possible to maintain either a constant reservoir level or constant wet well, but flow rates do tend to fall with time, so limited pump off on operation will likely occur. However, pumping system is essentially matching. I won't even go through the explanation of it, but there it is. You can actually set a target and have the system shoot for it. And what you're looking for is an average flow rate throughout the day, either outflow if you're pumping into a reservoir, inflow if you're pumping to a treatment plant, such that you get nice steady conditions. So you program for that so it'll hit a set point with a flow meter. You've set a set point, you have a flow meter. But basically what happens if you go too high or too low? Well, you can set it up in such a way that the level control has a high set point and a low set point. And if you get beyond the high set point, then it will start to control and slow the pump down so that you don't exceed that. Or if you go below, then it will speed the pump up. It's a fairly complex little thing, but it can be done. And there's a good description of it. And I say these are just things you should know are there in case you ever run into it. Alrighty, I do appreciate, and that should do